Hello everyone, welcome to a new lecture in the series of AI using Python. In the previous lecture, we have discussed Principal Component Analysis or PCA, which is a linear dimensionality reduction approach. In this lecture, we will be discussing Autoencoder, which can be considered as the nonlinear extension of PCA and are used for nonlinear dimensionality reduction. Similar to PCA, Autoencoder also considers unsupervised learning, in which the training data consists of capital N observations, where each xk contains of small n number of variables. In autoencoder, we transform the input vector into a latent space using a nonlinear transformation, and then we reconstruct the input vector from the latent vector. Autoencoder can be considered as a deep neural network consist of two subnetworks, which are called encoder and decoder, where in the encoder, the input vector is transformed into a latent vector y, where y is equal to e of x, where e is the encoder function and theta e contains all the parameters in the encoder function, which consist of the weights and biases of the encoder subnetwork. Here the latent vector y considered to be an m-dimensional vector, where small letter m is assumed to be less than or equal to the input dimension n. And the decoder will reconstruct the input vector from the latent vector using a decoder function, where x hat denotes the reconstructed input, d is the decoder function, y is the latent vector, and theta d contains all the parameters in the decoder network, which consists of the weights and biases of the decoder subnetwork. The optimization problem for AE is to find the optimal parameters theta E and theta D of the encoder and decoder network so that the reconstruction error is minimized. An autoencoder can achieve dimensionality reduction if it can able to reconstruct well the original data with the small letter m is strictly less than small letter n. This figure shows a schematic representation of the autoencoder, where the original input data is transformed into a latent vector using the encoder function, and from the transformed data we reconstruct the input data using the decoder function. Here we can see that if the number of variables in the latent vector is less than the number of variables in the input vector, we have achieved dimensionality reduction, and in that case we can use this latent variables, which can also called as features extracted from the input variables, for modeling purpose, such as the input data in regression problems. Next, we illustrate autoencoder using a numerical example, where we use the same example from the previous lecture. And first we can import all the libraries. And here for implementing autoencoder, we will be using the Keras library, where we use the dense function for defining neural networks. And here the input data is same as the previous lecture, which consists of 100 samples of 10 variables, where we have 4 linear relationships in the data and 2 nonlinear relationships. Now in the autoencoder, we select the dimension of the latent vector 6 and we can normalize the data. In the encoder function, we will be considering there is one hidden layer with the TANH activation function, and there is one output layer with the linear activation function. Similarly, for decoder, we will be considering there is one hidden layer with the TANH activation function, and there is one output layer with the linear activation function. Now this autoencoder will consist of combining this encoder and decoder function, and you can optimize the parameters in the autoencoder by using some optimization algorithm. Here we will be using Adam as the optimizer, and the loss function is considered as mean square error or MSE. Then using the input data, we can train the autoencoder model. Once the model is trained, we can predict the output, which will give x hat. So here this training will take some time because we will be solving a nonlinear optimization problem. And here we can specify the number of epochs in the optimization problem, which is here defined as 100. You can find the MSE for autoencoder using mean squared error function, which gives MSE AE as 0.0548, which is same as the loss function which we obtained here. For the trained autoencoder, we can plot the input data versus the reconstructed input. So in this plot, we shows the first variable in the input data x1 versus x1 hat. So here the x1 is plotted in red color and x1 hat in green color. So we can see that the prediction is somewhat okay. So here one important thing to observe is that the optimization problem for autoencoder is a nonlinear optimization problem, which can be a non-convex optimization problem. Therefore, the solution of the problem will depends on the initial conditions. and also the number of epochs. For different initial condition, we will be getting different solution. Therefore, if we try to rerun this code again, we might be getting a different solution, where we can see that the final accuracy is like 0.09, which is worse than the previous run. And we can plot the input data versus the reconstructed input in this case, which is worse than the previous one. When we can also try this by increasing the number of epochs and see whether it will give better results. So here we just increase the number of epochs into 1000. We can expect that if we increase the number of epochs, the solution might be better. We can also try with different values of hidden layer sizes and different layers in the neural network. So the key idea is that if the encoder can capture the nonlinear relationships in the data, it can able to reduce it into a lower dimensional manifold. Thereby it can achieve dimensionality reduction. After 1000 epochs, it got completed. Now we can find the MSE for this new model. So it is 0.003, which is very small. And if we see the plot of the input data versus reconstructed input, it looks almost perfect. So this means that if we train the autoencoder properly, it can achieve dimensionality reduction in a very good way. We can also try to do the same with the dimension of 4 and retrain the model with the number of epochs equal to 1000. It may take some time, but if the model is trained properly, we can see that the reconstruction error will be much lesser. And here the model got trained, and with the trained model, we can see that the error is like 0.002, which is very small. And also we can see that in that case, the plot of input data versus reconstructed data. So the reconstruction is very accurate. The advantage of autoencoder over PCA is that the autoencoder can able to perform dimensionality reduction well in the case of nonlinearly related data as well. But the disadvantage is that it is computationally more complex compared to PCA. And also its solution will depends on the initial condition. So we have to train it properly so that it will give better performance. Whereas in the case of PCA, it is a nonlinear optimization problem, which we can also convert into an eigenvalue problem. So it is computationally very faster and can be easily implemented. In short, in the case of data which contains large number of nonlinear relationships, autoencoder will be a better option compared to PCA. That leads us to the end of this lecture. Thanks for watching.